Hey everyone, welcome to a new episode of Calculuscious Explains It All. With me, Calculuscious, aka Mathy Cathy. You can call me MC. No, don't call me MC. That sounds too much like MC Hammer. Ooh, I am rocking these puffy pants today though. No, sorry. Now, despite the name of this series, I am actually, unfortunately, not going to be able to explain all of everything. However, what I will do is explain just enough of something to give you a good foundation and hopefully make you want to know more. The second episode is all about continuity. Specifically, what we will be discussing in this video is the definition of continuity at a point, which is a really important definition to know as you learn calculus. So let's go. Ooh, that reminds me. A couple of years ago, I had this algebra class that, I hate to say this, but they were kind of dull, except for one kid. This one kid, he just every time I told the class what we were going to do for the day, or whenever I handed something out for them to work on, he would always say, "Let's go." And he just had this energy that carried the class. So I don't ever think I got to thank him for that. So if you're watching, Lucas, thank you. Your energy was amazing. All right, now let's really go. So prior to studying calculus, I would assume that you have heard of continuity and related terms like continuous function and points of discontinuity. However, in my experience, the pre-calculus definitions prior to learning limits are always pretty fuzzy. Here's some that I've come across in my experience. A function is continuous if you can draw it in one motion without picking up your pencil. I never really felt great about that one. A continuous function is one with no breaks in the graph. Okay, again, I don't feel like that tells you a whole lot. And this is my favorite one, no discontinuities. There you go. Okay, so, those were probably okay for what you had to do with continuity prior to taking calculus. However, as we continue on, it'll be important to understand this definition, this limit definition of continuity. And it's one of my favorite definitions for whatever reason. I don't know, maybe because it has this limit in it and a function value. I don't know. Okay, I probably say that about everything. I probably say that everything's my favorite and I don't even realize it. So take it for what it is. But here it is, the definition of continuity. A function f is continuous at a point x equals c if the limit as x approaches c of the function exists. Number 2, the function value exists. And number 3, which is saying that just the first two things are equal to each other. The limit as x approaches c of the function is equal to the function value. So what we're going to do now is apply this definition. So we might have to go back to it a few times. We're going to apply this definition to numerous examples to show how it works. Okay, the first one is a series of graphs. 2 of them have discontinuities, 1 does not. And I just want to show you how you would set up the definition of continuity for those points. So what we are specifically looking at here, let me grab my stuff. Okay. What we are specifically looking at here is the limit as x approaches 1 and the function value at 1. Okay, we're going to focus on the point x equals 1 for all of these. So I'm going to grab my pen as usual. It is probably, oh my gosh, it's set up correctly today. Nope, see that? I pick a different color and it's all wrong. Okay, what we're going to do is set up, so let's just say here we're looking at x equals 1 for all of these. And again, what we're going to do is just set up a limit as x approaches 1. This first graph is the graph of f of x. And I hope that you can see from the graph fairly easily, approaching from the left and approaching from the right, that the limit would be equal to 2. Remember, a limit exists if your left hand and right hand limits are the same, and here they are both 2. You could also see that pretty easily with a little bit of algebraic manipulation. If you factored the difference of squares in the numerator, you would get x plus 1, x minus 1. And you could cancel the x minus 1 factors and then sub 1 in. 1 plus 1 gives you 2. Okay, so the first part of the definition holds. However, the second part of the definition is looking at the function value at the point. So again, we're looking at x equals 1, and there is no closed point for this function at x equals 1, so we would say that f of 1 does not exist. Since f of 1 does not exist, that's enough to say, therefore, f of x is not continuous. Continuous. I have to say it sometimes to know how to spell it. F of x is not continuous at x equals 1. So again, we were focusing on one specific point, x equals 1, and we just showed that the definition of continuity at that point does not hold. Again, in part B, I'm just going to try to draw a little line here. In part B, we have a discontinuity, but it'll be a little bit of a different reason. So let's take a look at this one. This is the g of x function. What I hope you can see is that the limit as x approaches 1 of g of x is still 2. The graph is going toward a y value of 2 from the left and from the right. Also, you would be using this part of the piecewise definition, which is the same as our f of x, for all points that are not exactly at x equals 1, which would be our limit. And so again, that limit is equal to 2. However, our function value this time, f of 1, nope, not f, g, I always do that. G of 1 is this closed point here on the graph, which has a y-coordinate of 1, or you could, look at your little piecewise equation down here, and it tells you that it's going to have a value of 1 when x equals 1. So both the limit and the function value exist. However, they are not equal. The limit of g of x as x approaches 1 does not equal g of 1. It's supposed to be a does not equal sign. So therefore, g of x is also not continuous at x equals 1. Finally, this last little example is one where the function is continuous at x equals 1, and let's show why. The limit as x approaches 1, this is a h of x function. Well, you could just plug 1 right here. 1 plus 1 is 2. Look at the graph. It's going to a y-coordinate of 2. And that also happens to be where the closed point is, so we will say h of 1 is also 2. And since we get the same value for both of those, we could say, therefore, h of x is continuous at x equals 1. Okay, so this was just a little beginning example to show what you need to set up for a particular point to use the definition to determine whether it is continuous at that point or not. If you are taking AP calculus, sometimes this is a really important thing to know because it'll ask you to justify your answer, why a point is continuous, or eventually you'll hear the word differentiable, and continuity is a part of that. And justifying your answer would be applying the definition as we did it here. Okay, so let me go back one more moment. F of x and g of x, they both had discontinuities, and they both looked they each looked a little bit different, but they are actually the same type of discontinuity, and that is called a removable discontinuity. Non-removable discontinuities are these other three. So if you take a look at this graph, what you're seeing here is a jump discontinuity. This graph, what you're seeing here, we call an infinite discontinuity, or that's also called a vertical asymptote. And then finally, there is such a thing as an oscillating discontinuity, which we actually won't see any examples of in this video, but I wanted to put it out there that it exists. Okay, these three, a removable, a jump, and an infinite discontinuity, we can see pretty easily from limit values what type of discontinuity we have. And so that's what we're going to be talking about for the rest of this video. We're going to be talking about looking at the definition of continuity at a particular point, and by using that definition, determining what type of discontinuity we have. So again, we're going to start with something fairly simple where we are going to use the definition of continuity at two particular points here, but we're going to use it to show the types of discontinuities that we have. Oh, this always happens to me. There we go. Okay, so let's just call this function y equals f of x. It's not really defined here, but we can define it there. And at first I'm going to look at x equals 1. What's going on there? Because I can definitely see from the graph that there's a discontinuity. Okay, I want to show you with the definition of continuity at a point what type of discontinuity it is. Okay, so what I'm going to do is I'm going to first start with my limit as x approaches 1 of f of x. However, what I want to do this time is I want to set that up and show the limit as x approaches 1 from the left and the limit as x approaches 1 from the right. And I'm doing that because I can pretty easily see from this graph that I have two different one-sided limits, and that'll set this limit up to be does not exist. But I think you should show that work. And so let's take a look at the limit as x approaches 1 from the left. So as you approach x value of 1 from the left, you are going toward a y coordinate of 0. So that's your left-hand limit. As you approach x equals 1 from the right, you are going to a y coordinate of 1. So since the left-hand limit and the right-hand limit are not the same, you're going to go back over here and say that your limit as x approaches 1 of f of x does not exist. And since the limit does not exist, that's enough to stop. I'm not even going to consider the function value at x equals 1. I'm just going to stop right here and say, therefore, that means that f of x is not continuous at x equals 1. And because my left-hand limit and right-hand limit are finite numbers, yet they are not the same, we can say that that means that there is a jump discontinuity there. Okay, so again, a jump discontinuity, I tell my students to find it graphically by looking for that gap in the graph, jump or gap. However, the way that you want to set it up by definition is you want to show that the left-hand limit and the right-hand limit are both finite numbers, but they are not the same. Next, let's move on to x equals 2. And what's going on there? Okay, so this one's similar to I guess it would be the second example that we looked at in the first exercise, where we have a limit value. The limit as x approaches 2 of f of x. Okay, if you would want to split it up into your left and your right to show that they match, you could. I'm just going to say it from here. I notice that the left-hand limit is a y value of 1. The right-hand limit is a y value of 1, and so that is my overall limit. Okay, however, f of 2, meaning where's the closed point when x is 2, it's up here at a y coordinate of 2. And since these do not match, we can say that f of x is not continuous at x, look at that, at x equals 2. However, the type of discontinuity is different. Since your first limit exists here, you are going to, but it's not equal to the function value, you're going to call that a removable discontinuity. Okay, so far we've seen two examples where we're looking at a graph and we're applying the definition of continuity at particular points to determine whether the graph is continuous or not continuous at those points. What we're going to do now, I'm going to come back because I have more space now. Okay, here I What we're going to do now is we're going to look at some functions just in equation form, and we're going to talk about how we can determine, whether a function is continuous or not at particular points, and what types even, just from looking at the structure of the equation, hopefully. All right, let me get set back up here, and let's take a look at this next example, g of x. So what we have here is a piecewise defined function, and what I always tell my students is first you need to look at each piece and ask yourself, would there be any discontinuities if I was only graphing each piece separately? So x squared minus 4, the domain is all real numbers. We know that that's a continuous function. It's a parabola, right? No breaks in the graph. X plus 2, the domain is all real numbers. There are no breaks there. So if we were graphing these separately, we would have continuity at every single point. However, since this is a piecewise and there is this boundary point of x equals 3, it could possibly have a discontinuity there at x equals 3. And so that's the point that we're going to focus on. I don't trust that this is set up correctly for some reason. Right, I think. Okay, what we're going to do here is we're going to talk about x equals 3 and what's going on there. So what I suggest you always do to start whenever you're trying to determine continuity at a point for a piecewise is you set up the left-hand limit and the right-hand limit, because that's pretty important for a piecewise to make sure that as you are approaching 3 from the left and as you are approaching 3 from the right, you are getting the same value, okay? And so where we have the definition of our function less than 3, that is what you are going to use for your left-hand limit. Less than is left, right? So all I'm going to do here is take x equals 3 and sub it into the less than piece of this piecewise. So I'm taking 3 squared minus 4. Okay, what is that? 3 squared minus 4 is 5, yeah. And now let's do the right-hand limit. Whenever you are greater than 3, you are to the right of 3, so you can take your greater than piece of the piecewise, sub 3 in. So I'm going to do 3 plus 2. 3 plus 2 is also 5, and so far we have a good start. We can see that the left-hand limit and the right-hand limit are the same, and therefore the limit as x approaches 3 of g of x does exist, and it is equal to 5. Now remember, that is just the first part of the definition of continuity at a point. We just established number 1. The limit as x approaches, in this case it was 3, of our function exists. What we now need to do is look at the function value at x equals 3 and ensure that it exists, first of all. And then we want to see if it's equal to 5. So up here I'm going to write now, what's g of 3? Okay, well, to find g of 3, if you're not looking at a graph where you can't find where the close point is, what you would do is see where is g defined at x equals 3. You're looking for the equal symbol. And so in the right-hand piece, notice that you have this equal to. That tells you that that is how you are going to define the function at x equals 3. And so I would calculate g of 3 by subbing 3 into the right-hand piece, because it's actually the greater than or equal to piece, and I get, again, 5. And so what I'm showing you here with this example is actually one where our function is continuous at the point that we were considering, which was x equals 3. Now, since it's continuous there, we can say that it is continuous everywhere because the domains of our pieces are all real numbers. There's no other points that could possibly be discontinuities. Let's look at another example of a piecewise defined function and see what happens here. Let's get another color. And again, set up your definition of continuity with first your left and your right hand limits. This time we are looking at the limit as x approaches -3 from the left, the limit as x approaches -3 from the right, and then finally we'll look at f of -3 and see if it all matches up or not. -3 is the point that we are, in particular concerned with here, because that's the boundary point of the piecewise function. So the limit as x approaches -3 from the left of f of x would be found by subbing -3 into the left-hand piece. 2 times -3 plus 14 is equal to what? 8? I think that's good. Set up your right-hand limit. For the right-hand limit, you're going to use the greater than piece. So sub -3 into 16 minus 2x. 16 minus 2 times -3. What's that? Let's see. That's 16 plus 6, so 22. And so right here we can stop and we can say, okay, there's definitely a point of discontinuity at x equals 3. Okay, I don't need to go any further. I could say that the limit as x approaches -3 of f of x does not exist, which means that my definition of continuity at, that's an n, just so you know, my definition of continuity at that point fails, and so it is not continuous. F is not continuous at x equals -3. Oops, I forgot the word continuous. There we go. Once again, though, remember that you could say a little bit more about that point of discontinuity. Specifically, you could say what type of discontinuity it is. So notice that your left-hand limit exists, it's a finite number. Your right-hand limit exists, it's a finite number. But what's happening is you have that jump going on, that gap between those two pieces. They're not matching up nicely. So this is not a removable discontinuity. It is a non-removable, and specifically, it is a jump. Next, let's take a look at a couple of examples of rational functions, and we'll talk about what types of discontinuities we can see here. So in this next example, I'm looking at h of x equals 2 over x minus 5. And something that you should consider when looking at a rational function is, are there any x coordinates that would make your denominator equal to 0? Because those would definitely be restrictions. So what I would start doing here to begin is I would say, what are the restrictions? What is x not allowed to equal? We have one restriction here, and it is x cannot equal 5, right? 5 minus 5 gives us 0. So that is the point that we're going to focus on, and we're going to apply the definition of continuity at that point to see what's happening. Now keep in mind, if it's a restriction, it is going to be a point of discontinuity, but I want to show you a little bit more about how it fits into this definition and what you can conclude about the type. Okay, so what I'm going to do is, similarly to how we approached the piecewise functions, I'm going to set up a left-hand limit of the function. This time it's h. And I'm going to set up a right-hand limit and see what happens there. You're not sure where to start, with these types of things. Start with that, setting up your left-hand limit and your right-hand limit. And so what I'm noticing here is that I can't use substitution to plug 5 in, right? But if we thought about what would happen if we do sub in 5, 5 minus 5 gives you a 0 in the denominator. However, you do not have a 0 in the numerator. So this is not actually a 0 over 0 situation. That may lead you to a specific type of discontinuity that you should be thinking about. Starting out, you might not realize this, but I'm telling you this now. What you should be thinking about here is whether this has a vertical asymptote at x equals 5, or we would call that an infinite discontinuity. It does. Okay, so what we want to think about with our left-hand limit is what's going to happen if I plug in some numbers that are a little bit less than 5, because those would be numbers that are to the left of x equals 5, and I get closer and closer to x equals 5. So maybe you want to start with something like x equals 4.9. What happens there? Okay, well, 4.9, I don't know if you actually want to write all this out or not. We'll write a little bit of it. 4.9 minus 5, what's that? Negative 0.1, and 2 divided by negative 0.1 is 20. Okay, let's get a little bit closer to x equals 5, but still stay less than it. So let's do like 4.99. Oh, I'm sorry, I said negative 20. There we go. 4.99. 4.99 minus 5 is negative 0.01, and 2 divided by negative 0.01 is negative 200. You might realize at this point that there is a little bit of a pattern here. The next one, if you did 4.999, would be negative 2,000. And so what's happening as x approaches 5 from the left is that you are going toward unbounded negative values, which we would call negative infinity. Now, just that right there, having a left-hand limit that is infinite, is enough by definition to say that you have the type of discontinuity you have here at x equals 5 is a vertical asymptote. H of x is not continuous at x equals 5, and it is an infinite discontinuity. I will do the right-hand limit just because we might as well. And so for that limit, you would want to plug in values of x that are close to x equals 5, but greater than x equals 5. So you could do values like 5.1, 5.01, 5.001, and see what happens here. And what you're going to find is that you're going to end up with 20, right? No negatives this time, 200, and 2,000. And so as x approaches 5 from the right, what's happening here is that you are approaching positive infinity. And finish off what I typically write. So this is approaching 5 from the left. We got negative infinity. This is approaching 5 from the right. We got positive infinity. And so now we can definitely say for sure that h of x is not continuous at x equals 5. And the reason is an infinite discontinuity. Okay, so what we're going to do now is we're going to wrap up with one more example. This is, again, a rational function, and it's going to take us through an infinite discontinuity again, and then it's going to go back one more time to removable discontinuity. So we'll see that just one more time before we go. This g of x function is defined by x minus 6 divided by x squared minus 14x plus 14. And remember, what I said about rational functions is that if you have a rational function, you should be looking at restrictions, specifically what makes that denominator 0. So let's factor this denominator. We get to factor here. Isn't that fun? Okay, let's think about this. Numbers that multiplied in positive 48 up to negative 14. That would be negative 6 and negative 8. Now, before you do anything else, stop there. We just wanted to look at the denominator in factored form to determine our restrictions. There are two. X cannot equal 6, right? Because 6 minus 6 is 0, and multiplying this entire denominator by 0 would make the denominator 0. Also, x cannot equal 8 because of the same reasoning. 8 minus 8 is 0, and multiplying by 0 would make the entire denominator 0. So those are your restrictions. And so those are the points that we're going to focus our definition of continuity on to show what types of discontinuities they are. Let's start with the x equals 6 discontinuity. Okay, what you want to do here is set up your limit as x approaches 6. I'm sorry, I got distracted. And this time, I'm going to suggest that you don't split it up into a left-hand limit and a right-hand limit, and here's why. I'm looking at my function, and specifically I'm looking at this factored form, and I can see that the x minus 6 factor, that's what I was getting distracted by before. The x minus 6 factor, it can be divided out of the numerator and denominator. And so my simpler form of this function, my simplified form, is 1 over x minus 8. So I can use that to find the limit as x approaches 6. I don't need to think about a left-hand limit and a right-hand limit here, because subbing 6 in to my simplified form works. Okay, it didn't work here, and I guess I should have talked about this. If we go back to this form, 6 minus 6 gives you a 0 in the numerator. 6 minus 6 gives you a 0 in the denominator. And so what you're seeing there is a 0 over 0 situation. And so you could use some algebraic manipulation to take you to this point, and then subbing in 6 does work. And we get a limit value of -1/2. So again, we didn't need to set up a left-hand limit and a right-hand limit, because we could use the simplified form of g of x to sub 6 in, and it worked. Okay, that is our limit value at x equals 6. And we already know that the function value at x equals 6 does not exist. I should say and. G of 6 does not exist. We know that because it's a restriction. Okay, if it's a restriction, the function value doesn't exist. And so therefore, we are going to say that g of x is not continuous at x equals 6. However, the reason is a removable discontinuity. You have a limit value that is a finite number. It exists. However, you have a hole specifically on the graph at x equals 6, and we would call that a removable discontinuity. For the other one, x equals 8, if you approach it the same way, you say, okay, let's do the limit as x approaches 8 of g of x. But let's try that simplified form. You're going to still see that that doesn't work, right? We can't sub 8 in to this simplified form still. The x minus 8 factor did not cancel out. And so that should lead you to believe that what's going on here is an infinite discontinuity or a vertical asymptote. And so you, at that point, could say, let's set up a left-hand limit as x approaches 8 of g of x. And through some numerical reasoning, you would find that it's equal to -infinity. Set up a right-hand limit as x approaches 8 of g of x. Again, through some numerical reasoning that are similar to, what we did here in this example, you would see that that one is equal to +infinity. And so we would say, therefore, g of x is not continuous at x equals 8. But this time it is because it is an infinite discontinuity. Okay, so I hope this was a good starting point for you, and what you're going to see as you continue to study calculus is many theorems are dependent upon a function being continuous at the points that you're trying to apply the theorem for. And eventually you're also going to see a word called differentiability, or you'll hear, is a function differentiable or not? And continuity is a part of that. So understanding this definition of continuity at a point will be very helpful whoops, where is it? There it is. It'll be really, really helpful as you continue your study of calculus. And understanding these types of discontinuities and how you can set up that definition to show the different types of discontinuities will come in really handy. So I hope this was helpful. Good luck in your studies. Bye.